So what I'm going to be discussing today is modeling strategies to use electronic medical records data to determine who we want to genotype for a preemptive genotyping program. And this is a joint effort with people that I'll in several different departments. So there's a large body of literature that relates genetic variation to medication responsiveness. There's well over 100 drugs that have pharmacogenetic information in the FDA labels. In addition, in a cohort of 53,000 what I'll call medical home patients at Vanderbilt, and I'll describe what that means in a little bit, we estimated that over a 5-year time frame, 65% of those people would get exposed to at least one medication with an FDA label, and 23% of people would get exposed to at least 3 medications with FDA labels. So the idea is that you have a lot of people getting exposed to a lot of medications with these pharmacogenetic information on their FDA labels, and in fact, people are getting exposed to multiple such medications. And so that's sort of the impetus for the PREDICT program, which is a quality improvement initiative to use preemptive and panel-based genotyping in order to deliver genotype-tailored therapies. So there are a couple of important features of the PREDICT program. First of all, it's preemptive. That is, we want the genetic data available in the electronic health record prior to prescribing so that we can use it immediately. And it's panel-based. That is, we want to genotype from we want to do genotyping from many genes and many functional polymorphisms so that we can reuse the data if somebody gets prescribed another medication that has a pharmacogenetic effect. So when we were developing the PREDICT model, we used electronic health records data to identify the people who are at high risk for getting prescribed a pharmacogenetic medication. That is, we wanted to identify the people who are at high risk for benefiting from having their genotype on file. And so what we did is we constructed a risk prediction model to calculate the future risk of getting put on either a statin, warfarin, or antiplatelets. And it was implemented into a clinical decision support tool that was incorporated into our electronic health record. And that is, prior to patients going to their clinic visits, the patient-specific risk of getting put on one of these medications was calculated, and the physician was alerted if the 3-year risk was greater than 0.4. They said, okay, this patient is at high risk for benefiting from a preemptive genotyping program. And so they would recommend genotyping for those people. So this brings us to a project that I'm working on now, which is called the Rational Integration of Genomic Healthcare Testing. It's a collaboration of people like me, I'm a biostatistician, health economists, physicians, and informaticians, to evaluate the feasibility and cost effectiveness of different flavors of pharmacogenetic testing strategies. The PREDICT program is one of those examples. It's a preemptive and panel-based genetic testing, but you can imagine you might also think about using reactive testing programs where you wait until somebody gets the indication and then you decide to do the genetic test. You can have different sorts of hybrids from different models. And what we're doing in the RIGHT project is we are comparing different approaches using discrete event simulation, that is, using Vanderbilt estimated parameters as well as literature-based parameters. We can simulate a population over time under a lot of assumptions that include, like, what are the medication exposure rates, what is the risk conferring variant allele frequency, how often do medication failures occur, et cetera. And over time, well, what the discrete event simulation will do is it estimates the accumulation of like adverse events or quality adjusted life years and costs and deaths, et cetera. And then so we can conduct these discrete event simulations under different sort of pharmacogenetic testing strategies. And then we can compare them. And that's what the ultimate goal of the RIGHT project is. So now, depending on the rate at which genetic testing results can actually be returned, like in real time, and utilized, a reactive strategy can be sort of logistically challenging. So I'm going to continue to focus on, at least for today, I'm going to discuss preemptive panel-based testing and improvements that we've been making over the original PREDICT approach. So with PREDICT, what we said is we estimated the risk of having an indication for one of these 3 medications, and if that risk was greater than some number, we said, do a genetic test. So we can improve on that in a lot of different ways. We can make a lot of modeling improvements. For example, our EHR has evolved, and now we can incorporate a broader set of independent variables, so we should be able to make more accurate predictions. In addition, as opposed to building one model for, are you going to get put on one of these 3 medications, seems pretty obvious to build medication-specific models. You can imagine how much that's going to increase your accuracy. And what I also wanted to do here is consider machine learning techniques to see if they would beat out the approaches that we had been using. So we believe we can improve modeling, the modeling approach. We also believe we can improve the decision-making approach, and that is by incorporating medication-specific genotype-associated utility gains into our decision. That is, how important is it for this person to have their genetic information on file for this medication? How important? Well, we want to incorporate the importance of having their genetic data on file into our calculation of who should we genotype. So this is a little bit of an outline. What I first want to do is describe who our medical home cohorts are. There are going to be 3 of them. We're going to build a model for antiplatelets, statins, and warfarin, and I'll talk about the variables that we're incorporating into those models. Then I'll talk about the modeling strategies and how we evaluate the models to predict the risk of a pharmacogenetic medication prescription. Again, we're trying to predict we're trying to predict a medication prescription or an indication for a medication prescription. So we're going to do that with a Cox model, and then as well as with random survival forests. And then I want to talk very briefly, and this is still unfinished work, so I'll just kind of give an example of how it might work out, the incorporation of utility into the decision-making process of whom we want to genotype. So the medical home, we define our medical home population as those who've had at least 3 outpatient visits within a 2-year time frame in these non-acute clinics. The patients must satisfy that medical home definition for the first time between July of 2010 and March 2013, and then we follow them until July of 2014. So that's sort of that defines our cohorts. And for each medication that we're studying, you had to have been, as far as the electronic medical record is concerned, you had to have been naive to that medication in order to be included in that cohort. So these are our 3 different cohorts, and they're largely overlapping. We have approximately 20 to 25,000 people. For continuous variables, I'm showing the median and the interdecile range. So on average, the median is approximately 50 in these cohorts. 60% females. We're incorporating some vitals data like systolic and diastolic blood pressure. We also have lipids data available on 18 to 19% of people. We have HbA1c data available on approximately 6% of people, and these are the values among the people who we have those data on. And then we wanted to incorporate medical history. 6% of people approximately had a history of type 2 diabetes. 30 to 35% of people had a history of hypertension. And an important predictor, which is obvious in retrospect but wasn't incorporated in the original predict model, is what clinics are they actually going, what's the clinic that they're going to? So 40 to 45% of the people that we observed were going to cardiac clinics. 1 to 4% of them had a history of an acute cardiovascular event. So this is the cohort that we're studying. These are the cohorts that we're studying, and these are the rates at which they're getting put on these medications. So this is antiplatelet therapy, statins, and warfarin. And by 2 years, approximately 7% of people, so at 730 days, approximately 7% of people are expected to be exposed to antiplatelets, 18% exposed to statins, and approximately 8% exposed to warfarin. In considering, so now we want to model the risk of getting put on these medications. So since follow-up times are highly variable, we want to use time to event analyses. And so one of the obvious approaches would be a Cox Proportional Hazards model. And from the Cox Proportional Hazards model, we would summarize the non-parametric estimate of the baseline hazard as well as the parametric portion of the model. And ultimately, we want to get the risk of getting prescribed a particular medication by some time in the future, given your covariate values. So say, what's your risk within 2 years of getting prescribed a particular medication? That's what we're ultimately attempting to get here. Random survival forest is another way of approaching this. It's a very popular ensemble-based machine learning approach, and we're going to consider the same set of independent variables. There are a number of tuning parameters that you need to consider when you're using random survival forest, and I'll talk about those in a little bit. So basically, you have a forest, and the forest is made up of a bunch of trees, and each tree provides a predicted value for each person. And then the final predicted value for an individual person, or for an individual, is taken by averaging across all the trees. So you get an averaged across trees predicted value for an individual. So these are the results from the Cox model. Let me just, these are different, this is the warfarin model, the statin model, and the antiplatelet model. As you can see, these, we have quite a few different exposure variables. And we're allowing the functional forms of the covariates to be nonlinear. So on the y-axis are hazard ratios. And you can see that, for example, age, this is clearly a nonlinear effect. If you're younger, then there's a big effect of age. But once you get to a certain age, the effect of age seems to plateau. So it's certainly a nonlinear effect. As you would expect, LDL cholesterol is a very strong predictor of whether or not you get put on a statin. Going to a cardiac clinic is a good predictor of whether or not you get put on a statin. Having a history of a cardiac event is also a good predictor of getting put on a statin. So these are the different models. In these models, these are estimated with the Cox Proportional Hazards model. We have 20 to 25,000 people in these data sets. The Cox Proportional Hazard model has no problem with these. We're estimating like 60 parameters. It's not a problem for the Cox model. These are the sort of the relative attribute strengths. I've sorted all the different variables by how important they are according to the likelihood ratio chi-squared statistic minus like a degree of freedom penalty. And you can see there are commonalities between these models. This is the antiplatelet model, the statin model, and the warfarin model. Going to a cardiac clinic is a good predictor of whether or not you're going to get put on one of these medications. Age is a good predictor of whether or not you're going to get put on one of these medications, but there are certain variables that are important for one of these outcomes, but not important for others. So for example, LDL is a strong predictor of whether or not you get put on a statin, but it's not so strong a predictor of whether or not you get put on an antiplatelet. So it's sort of a reason why you might want to split these models up. These are calibration plots for 1-year risk of getting put on these medications. And what you're hoping for when you look at these calibration plots is you're hoping that these colored lines fall right along this gray line. And to the extent that they do is to the extent that your predicted risk is actually equal to your actual risk. Each of these little X's represents 500 people. And so what you see is that for the most part, for the most of the distribution, our models are very well calibrated. But once you get into the high end, like the top 2% of people, our models start to over-predict a little bit. That is, our predicted risk is a little bit greater than the actual risk. For example, here, the predicted risk is around 28%, and the actual risk is around 23%. But it's not a severe over-prediction, and it's only for a couple % of our data. But all these models are really well calibrated. If you look at the C indices, which are a measure of discrimination for these models, you can see that in the original data sets, for the antiplatelets and statin models, it's about 0.78, and for warfarin, it's about 0.75. When you correct for model optimism by using a bootstrap or by using a X-fold cross-validation, you can see that these models are not overfit. There's very little need for correcting for model optimism here because we have, we have over 1,000 events per outcome. We're only estimating like 60 parameters, so the Cox model does great here. It's not an overfit model. So that's sort of the story from the Cox model. Now, let's change the focus to the random survival forest, and this is something that I was learning about as I was doing this project, actually. So there are a number of different tuning parameters for the random survival forest. For example, in your forest, how many trees do you want? For continuous variables, how much do you want to be able to split those continuous variables up? We'll call that n-split. The number of variables that are tested at each node within a tree, called m-trie, as well as the number of events that we permit in our terminal nodes of a particular tree. These are all tuning parameters that we wanted to study when we were building these random survival forests. So these are prediction error plots, and I'm defining my prediction error as 1 minus the Harrell C index. And so lower value is better here. And as you can see, if we don't have that many trees, then increasing the number of trees really improves our prediction error. It lowers our prediction error. But once we get to a lot of trees, then having more trees doesn't really help. So where we landed, considering computational time, is we landed at 200 trees. We're going to say, let's build these random survival forests with 200 trees. Then we wanted to consider all these other parameters, the number of splits for continuous variables, the number of variables tested at each node, as well as terminal node size. And what you see when you fit the original data using the C-index as your measure of sort of how well a model discriminates people who have events from those who don't, what you see is that if you use, say, 50 splits and you're testing 5 variables at each node and your terminal node size is 20, you can get a really great C-index. I mean, it looks great. The model looks awesome. Like, oh, I can really discriminate people who get prescribed this medication to those as compared to those who don't. However, when you start looking more carefully, you realize that the model is highly overfit. And so when you do 5-fold cross-validation, you can estimate how optimistic your model is, and then you can do the correction and get the corrected C-index. And the interesting thing that I found about this little exploration that I did is that you see a lot of the original C-indices vary a lot as a function of these tuning parameters. But once you correct for optimism, it really doesn't matter. All these corrected C-indices are approximately the same. So the tuning parameters, after doing corrections for optimism, really end up with the same results. The tuning parameters didn't have an impact on the corrected C-indices. And that was the case for all of the models. It was the case for the statin model as well as the warfarin model. And maybe it just means that we've gotten all the information out of these models and there's no more information to get. If you compare the corrected C-indices for the Cox model versus the random survival forest, you can see that they come up with just about the same answer. So this is a situation where doing a machine learning approach really didn't help over doing a standard statistical approach. And it's very possible that it's just because these models are just not that complex. The standard Cox model can totally handle it. There aren't complex interactions here. So that's sort of our model building approach. You could use either a Cox model or the random survival forest and get predicted risks for each person. And now what we want to start thinking about is how do we decide who to genotype? So for each medication, we can consider the risk score. What is your risk of getting put on one of these medications? And now what we want to incorporate is the utility gain associated with genotyping that person for that medication. So the utility gain would be the utility for the medication under genotype-tailored therapy minus the utility for the medication under a non-genotype-tailored therapy or standard therapy. And the difference between those two is the utility gain or the benefit associated with having genotyped somebody for that particular medication. If we sum across all different sorts of medications, we can get the expected utility gain for a person across all medications. So if we sum the risk of getting put on a medication times the expected benefit associated with having been genotyped for that medication, and we sum across all medications, we can get the expected benefit of genotyping that person. And so this will inform our decision-making process. We would like to genotype the people who are most likely to have the highest expected benefit. That's the approach that we would like to take. And so I want to give you a quick example. This is a result of a discrete event simulation. This is just work in progress, so don't take it too seriously. So let's pretend that we look at 2 million, we simulate 2 million people, either under a non-genotype tailored therapy or under genotype tailored therapy. That's what GTT is. Under genotype, so the standard of care is giving somebody clopidogrel after they have a stent. But some people have variant alleles, and so if we know what their genotype is, we might consider giving approximately 230,000 of these people the alternative therapy, which is prasugrel or ticagrelor. Now, for these 230,000 people, we're likely to prevent medication-related failures, but we're also very likely to cause some bleeding because they're better for these people, apparently, they improve failure rates, but they increase bleed rates. So if you look at non-fatal severe events, we estimate that we could prevent approximately 3,000 if we had done genotype-tailored therapy as opposed to not. And for fatal events, we estimate that in a population of 2 million people, we might be able to prevent about 1,100 fatalities associated with clopidogrel or antiplatelet therapy. So overall, if you consider severe events and fatal events, in a population of 2 million people, we estimate that we could prevent approximately 4,000 bad things from happening. So if you standardize that per 10,000 people, getting put on one of these medications or having the indication for one of these medications, we believe that, we estimate from this simulation study that we could prevent approximately 21 severe or fatal events from occurring. So this is all very preliminary, this is still a work in progress, but this is sort of how we're approaching this. So we can consider that. So if we consider this should be the utility here that I've been discussing is severe or fatal events per 10,000 people exposed to the medication. For antiplatelet, we just estimated that could be around 21. We're doing those for the statins as well as for warfarin as well, and let's just pretend that we know what those numbers are, and it's 12 for statins and 10 for warfarin. Then we can calculate the expected number of severe or fatal events prevented per 10,000 people getting exposed to these medications as the weighted sum of these utility gains or these expected benefits. And then we can create genotyping rules based on these expected benefits. So we could create a rule that says, okay, we're going to genotype people if the expected benefit is greater than 10 per 10,000 people. That is, for 10,000 people that get put on one of these medications, by doing genotype-tailored therapy, we might be able to prevent 10 bad things from happening, or 1 in 1,000. So in a population that was, in a cohort that was naive to all 3 of these medications, we estimated that about 1,300 people out of 17,000 would get identified by this particular rule, and their average expected utility is about 12.2 per 10,000. And so in these 1,315 people, we expect that we might be able to prevent 1 or 2 serious or fatal adverse events. Whether or not that's big is something to be discussed. And so there are a lot of different, we still have a lot of work to do on getting better estimates of these numbers. But I just want to show you among these 1,300 people, so you identify the 1,300 people, and then you say, what's the rates at which they get put on these medications? So remember, we had about a 7 or 8% rate in 2 years for antiplatelets and warfarin, and about 18% for the statins. So what this shows is by using this rule to identify the high-risk people, it shows us how much we're sort of enriching the pool of genotype people as opposed to doing just picking people randomly to genotype. So you can see about 17% of people are expected to be exposed to antiplatelets or warfarin within the next 2 years, approximately 50% to statins, and overall, we estimate that 60% of these people, of these 1,300 people that we've identified, would be exposed to at least one of these 3 medications. So we've sort of enriched the pool of people who were genotyped. Okay, so there are a couple of keys to the success of a preemptive panel-based types of approaches to genotyping. One is you need to build models that predict risk well, but there also have to be a number of medications that have pharmacogenetic effects. Over time, you're hoping that a high percentage of people are prescribed multiple such medications. As of now, since it's a little bit too expensive to genotype everybody, we're developing sort of a flexible approach to identify candidate patients for preemptive genotyping program. So the medication-specific models improved our discrimination, prediction, and enrichment over a single model. I didn't actually discuss the single model approach. But as of now, and in this particular setting, there does not seem to be a particular benefit to doing a machine learning type of approach over a standard approach. We have plenty of data. And so our next steps are actually some things that we're working on right now is, we have longitudinal data on these people. So we want to exploit the longitudinal data that we already have. We want to validate these models in a population from a more recent time frame. So we looked at people up through July of 2014. So we have newer data that we want to examine. When I discussed utility gains, I only talked about adverse events prevented. And really, the part of this project is very much about cost and quality adjusted life years. So those could be factors into how you decide whom to genotype. And ultimately, the goal of this particular project that I'm working on is to use these simulation studies to compare these different sorts of strategies for conducting genetic testing programs. So that's it. Thank you. We're in the medical school, or we're in the medical center, as opposed to, I grew up in schools of public health, where the Biostatistics department was in the School of Public Health. So it's a slightly different, we're within the medical center, and so it's